Now we may start. Again, good day to everyone. We will start with manifolds. Our first topic is...
Maybe I'm sorry to interrupt you, but maybe you can tell something about the plan of the course, the rules of the grade, and
everything is written in. You may find it in LMS system, but I can recall you, of course. We will have regular home tasks after each lesson, and we will have intermediate exam at the end of this module. This is end of October. And then you will have final exam at the end of semester. That is the end of the second module. The grading, the weight of, so let me write. So grading. So everything is written in LMS, but I will put into my Google account also a program, the program of my course, where you will see again this grading written. So you will see it. With weight 30% comes home tasks. So home tasks. Plus 20% for intermediate exam. Or just midterm exam, let me write. Midterm exam. Plus 50% for final exam. Both exams are written, okay? So at the time of exam, you will, each of you will receive 2 problems and do it during the time of exam, which will again take 1 lesson. Starts at 13 and ends at 16. Both exams are this. Besides, for people who are doing their home tasks well, I will suggest advanced exam. The rules for advanced exam, this will be a written exam, but you will take these problems for advanced exam to do them at home. And I will give you some 2 to 3 weeks for doing these problems. These problems are harder than ordinary problems in home tasks. And if you do them all, then there are 12 problems in this advanced exam. And if you do them all, then you obtain the maximal grade, 10 points. Otherwise, if it is smaller, then I will give you the scale of grading. But if you obtain less than 8 points for advanced exam, then you will be obliged to do usual final exam as other students, okay? I will recall you about advanced exam at the beginning of the second module. That will be the time, more close time to send you the problems for advanced exam. Okay. So is it clear?
Yes, the grading is clear. And
okay.
What about will the course be? It will be about manifolds.
Yes, mostly about manifolds, of course, because this is some more or less standard thing. And I believe that many of you know the things very well. Okay. But there could be certain people who are not much familiar with manifolds. So if you look at program, you will see that it concerns manifolds. Okay, there are several, there are, this includes many topics and the program which is written, which you will see in the Google account, and also I believe that it will be put on the website. I will make announcement later about that. Then you will see that this is a maximal program. So the real what we will achieve, it depends on time. So if time permits, we will do maximal program. But usually we don't cover all the topics. And anyway, the all home tasks and final exam and midterm exam include only those topics which are discussed on lessons, okay? So no more than you will hear on lessons will be included into your home tasks and exams. Okay, so let's start with manifolds. So manifolds and smooth manifolds. We will be, of course, doing smooth manifolds. I will shorten some words. Say manifold could be written as shortened as. Okay. So let's start. What is the topological manifold? Let me denote this as X. Topological manifold. This is the topological space. So which has an open cover by subsets, say UIs, where I runs through the set of indices, some set of indices, which could be any set. Big I could be any set. Open cover. Such that each UI is homeomorphic. So homeomorphisms will be denoted by this tilde. So homeomorphisms. Let me say open set in Rn. So in this case, we call X n-dimensional. N-dimensional. Topological manifold. So this is the first condition. And the second condition that it is Hausdorff. So the topological space satisfying the conditions A and B, where B is X is, oops, they also already say that we are out of time. Okay, X is Hausdorff. That means that any two distinct points could be covered, say X and Y, and X can be covered by disjoint open subsets, say U and V. That means the intersection is empty. There are sometimes some more conditions on the manifold. Say sometimes it is usually assumed that X is second countable. That means that it has a countable basis of topology. Or otherwise, the assumptions on X is to be paracompact, say. But all of them are necessary for doing the partition of unity. So if we need to have a partition of unity, which I will remind you later, on the manifold, then we impose some general conditions. It depends on our choice. Say when it is second countable, then it is automatically paracompact. So intrinsically, we could assume that the first condition is satisfied. For example, if X is compact, that means from any open cover of it, we can choose a finite subcover. Then it is automatically paracompact and second countable. Okay. Now, let me say about charts. So what do we mean by chart? So if this is our X, let me draw the picture. So charts. Or local charts. So if this X, if this is X, and we take by a local chart, or shortly by chart, we mean some open subset, say U in Rn, open, and a homeomorphism of U to onto say, let me denote it by phi, say phi of U, an open subset phi of U open in X. And we call this pair U and phi, call it the chart or local chart. Two charts let me take two charts from now on. Let me take two charts. Say, again, I draw this the same picture. So, say UI and another chart, this is X, another chart, say, this are both charts living in Rn. So Uj, and assume that the images under the corresponding homeomorphisms, phi I and phi j, assume they intersect then we take just the preimage of their intersection. So this is phi of ui, this is phi of phi I of ui, respectively phi j of uj. So if you take the preimage of their intersection, so this is phi I to minus 1 of their intersection. So if you have this one, respectively take the preimage of this of the same thing by phi j. Okay, so then we have a homeomorphism, since both phi I and phi j are homeomorphic. So we have the map which I could denote by as the composition of phi I and phi j to minus 1. So first phi I, and then phi j to minus 1, only restricted, of course, onto this pieces, phi to -1 of the intersection and phi I to -1, so respectively phi j to -1. So, but to shortly, without abusing, I mean, abusing notation, I just, sorry, I should change I to j. So, phi j to -1 times phi I, composition phi I. So we have this restricted homeomorphism. And let me give the definition. Two charts, UI and UI phi I and UJ phi j are called compatible if, yes. Okay, so let's continue. Oops. Sorry. Okay. So two charts are called compatible if this map, the restricted map phi j to -1 composition phi I. Let me for convenience denote these two pieces, this one as Uij and this one as Uji. Okay, so so this map is a map from the open subset Uij living in Rn to another open subset Uji, again living in Rn. So here in Rn you have coordinates, say x1 to xn, standard coordinates, respectively. In another Rn you have coordinates y1 to yn. So the map phi ij, which is the homeomorphism, is given by certain functions fi of x1 up to xn, and we impose the condition if the functions, I again shorten words, are infinitely differentiable. It is shortly denoted by C infinity. So infinitely differentiable. That means that their partial derivatives. There exist partial derivatives. Of all orders of any order. Then they automatically, these derivatives are continuous. So I just say, it is enough to say that there exists partial derivatives of any order K positive. And the inverse of this map, so this will be phi j times phi I minus 1, which is the inverse of the previous one, is also infinitely differentiable. Also C infinity map. So we have not only a homeomorphism, but what is called shortly a diffeomorphism. Shortly phi j to minus 1 times phi I is called diffeomorphism. So diffeomorphism. Okay. Now we are ready to define what is a smooth manifold. So before we do this, we only should give the definition of the atlas. So the definition. The collection of charts, say UI, oops, sorry. Of charts UI, phi I. Where I belongs to some set of indices big I, is called an atlas. Of X if this is the collection of charts. Of X is called the atlas, an atlas of X if any two of these charts are compatible. And they cover X in the sense that the images of these charts as open subsets in X constitute an open cover of X. Okay. We may say about the compatibility of atlases now. Say two atlases, let me denote this atlas shortly by A. Two atlases say A and A prime of X are called compatible. If the union is also an atlas. Of X. So now smooth manifold, X is called smooth manifold. If it admits an atlas. So we usually work with some given atlas in X, and mostly this atlas is given intrinsically, not explicitly. We just mean that there is certain atlas. Okay, if we take all atlases compatible with between themselves, the set of all compatible atlases, on a given smooth manifold, on a given manifold, on X is called a smooth structure. Smooth structure on X. So we, by smooth structure, we mean on X, we mean X with any of the set of compatible atlases on it. Of course, on a given topological manifold, there could be either several or more smooth structures. Why not? And there are examples. That means that there are certain collections of compatible atlases, say one collection of compatible atlases and another collection, such that no any basis atlas from first collection is compatible with some atlas from the second collection. That means that we have two distinct smooth structures. And we may ask the question whether there are topological manifolds on which there are not one smooth structure. Such examples exist. For example, on R4, there are many, but not only many, but infinitely many. This is a very strong result, infinitely many smooth structures. Other Rn have only one smooth structure. So this is just the an example. Okay, let us say what do we mean by a smooth map between two smooth manifolds. So if you have two smooth manifolds, say X and Y, take any open subset in X. This is as you know, the image of certain open subset in Rn under homeomorphism. So if this is, say, U, and here we take any open subset. So this is respectively phi of U. So we have corresponding chart. Here we have respectively, say, let me denote it by V. And assume we have a map from X to Y, a continuous map. So continuous. Since we are in the category of topological manifolds, the only maps which we consider are continuous. And assume that this is phi of, not phi, but let me denote it by psi. Psi of V. So assume that f of phi of U intersects psi of V. Since these are charts from atlases, we always can find such a chart, the image of which intersects the image of certain given chart in Y. So this is f of phi of U. Take the intersection, take its pre-image under f minus 1 of this, let me denote this W and take its preimage under, so let me denote this by, say, W tilde, and by W its preimage under phi. So we have W, which is by definition phi to minus 1 of W tilde. Respectively, here we have the preimage of W tilde in, so let me denote it by W prime, the preimage under psi. Okay, W tilde. So we thus have the map from here to here, which of course could be shortly denoted by the composition from right to left. We write it as phi, composition F, composition psi minus 1. So we have this picture. Okay. And the definition of a smooth map, a continuous map F from X to Y of smooth manifolds is called smooth if for any U chart, U phi, for any two charts in X, respectively Y, the map psi minus 1, composition F, composition phi, of W, which is obtained via these preimages of intersections, to W prime, is smooth. And you remember that by a smooth map between two open subsets in Rn, we mean a map which is given by infinitely differentiable functions. That is given by C infinity functions. Okay, so this is a smooth map. What do we mean by a diffeomorphism? A smooth map. A smooth map. F from X to Y of smooth manifolds, of course, of smooth manifolds. Manifolds is called a diffeomorphism. A diffeomorphism. I again shorten the words. If both F, if it is bijective, if F is a homeomorphism, that is bijective continuous map, such that both both F and F2-1, its inverse as a continuous map, are smooth. Let me just give you a trivial example of a map which is smooth but not a diffeomorphism. Say, let me take for X just R and for Y just R, and send X to X cube. Of course, R is has the only chart, just smooth chart, just coinciding with the whole R. So in this chart, we have coordinate X, and this map is clearly smooth. But of course, F-1 is not smooth at which point? You can guess easily that is not smooth at the point 0, because at the point 0, because F2-1 is given by taking the cubic root of Y. And this is not smooth at 0. Non-smooth at 0. At any other point, it is smooth, of course. So totally, anyway, this map is not a diffeomorphism. So F is not a diffeomorphism. Okay. So let us give some standard examples of manifolds. Just for example, smooth Rn is smooth manifold. And of course, second countable. That means that it has a base of open subsets which is countable. What is the countable basis of topology on Rn? These are this is given by open balls. Okay, we are again out of time. So we have to stop and it take me a certain time to gain to
И еще обязательно, чтобы у тебя была спецификация на бумаге, чтобы ты знал, какую пачку у тебя определилась. Ну давай, пока.
Okay, maybe we should continue. Do you see the screen?
Yes.
Okay, thank you. Just a moment. We stopped at the point that Rn is smooth and second countable. To see that it is second countable, it is enough to present the countable basis of topology in Rn. For this, we take open balls, the set of open balls with center at the point, say B, with coordinates x1 to xn, which all are rational, xi's are rational, and the radius, say r to be also rational. So all such balls constitute a countable set, and this is known to be, very well known to be the basis of topology, standard topology in Rn. Okay, more interesting example is, of course, the n-dimensional sphere, which is, or shortly n-sphere, which is given by the known equation, say, let us take Rn plus 1, where it lives canonically, and take the coordinates from x0 up to xn in Rn plus 1 such that the sum of squares of them is 1. So this is the unit sphere. How to obtain charts? There are two standard charts. Let me draw a picture. Given by, you should know this, I believe, very well, by a stereographic projection. So if this is coordinate x0, and these are coordinates xi's, then I from 1 to n, and then the sphere can be, you have two distinguished points, say 1, 0, comma, etc. 0. This is North Pole, and the South Pole, -1, etc. For you just take for a chart, you take for a first chart, you take S, so S minus, say, South Pole. The chart maps some open subset in Rn to certain open subset in our manifold, but we take the inverse map, say phi 1 to minus 1. So this is the map to the whole Rn, which is given by stereographic projection. So take any point x in the sphere and project it onto the point from the South Pole to the point, say, y. If x is the point x0, xn, then it projects, as you easily see, just to the point, say, x1 to 1 plus x0. Keep in mind that the denominator here is non-zero once we are outside the point, the South Pole, up to xn over 1 plus x0. Okay, respectively, the second chart, so the first chart is just U1, which is the whole Rn. The second chart is given by S minus North Pole. This is phi 2 to minus 1 to Rn, which is in this case the second chart. U2, which maps the point x correspondingly by the projection from the North Pole. So, oops, I'm sorry, my straight line is not straight enough. Okay, so to this point, say nu y to say y prime, which is, as you easily see, just x1 over 1 minus x0, okay, etc. xn over 1 minus x0, which is also well defined because you are outside the North Pole. Okay, so the sphere is covered at least by 2 charts. If we could cover it by 1 chart, which is Rn, then it would mean that S is homeomorphic to Rn, but it is not, of course, homeomorphic to Rn. So, by the way, Sn is clearly compact manifold. So, let me stop at this point for examples and say some general words about a few more words about manifolds. Say if x and y are smooth, x, y are smooth, then their Cartesian product or direct product is also smooth, since if we have charts, say ui, phi I, any chart ui, phi I in y, and respectively any chart uj, psi j in y, then the corresponding chart in x times y will be ui times uj, respectively phi I times psi j. That is clear. So it's a chart. These are charts in x and y, and this is a chart, corresponding chart in x cross y. Okay, of course, you have two projections onto factors. The projection onto x, say projection 1, and projection onto y, projections onto factors, or shortly natural projections. Then clearly these are smooth maps, projections. Onto factors are of course smooth. Of course, if you have a product of more than two manifolds, then smooth manifolds, say x1, what should we mean by the product of n, say m smooth manifolds? This is by definition, say x1 cross x2 cross etc. So x up to xn. And of course, this operation of taking successive direct products is associative. So you may change brackets in a way whichever you want. And after all, we just omit all the brackets and write this like this, without brackets. And of course, this operation is commutative in the sense that the two x cross y is diffeomorphic to y cross x. Diffeomorphism, contrary to homeomorphism, is denoted by these two tildes, two curly symbols. Okay, so this means diffeomorphism. So this is a canonical diffeomorphism. Okay, so we should speak a little about vector bundles over smooth manifolds. Vector bundles, it is very important notion. So what is a vector bundle? So let X be a smooth manifold. So the definition, X, let X be a smooth manifold. Sometimes I will omit the word smooth if it is clear from the context. Because we mostly work with smooth manifolds. By rank R vector bundle. So, shortly, I denote the word bundle this way. Rank R, vector bundle, E over X. This is a pair, is a pair E and the projection, say pi, from E to X. Where E is a smooth manifold. Okay, so they are warning that our Zoom will stop again in some 10 minutes. My apologies, but I have nothing to do with that. We will try again to re-enter again when it switches off. Where E is a smooth manifold, and pi is a projection, is a smooth map, and pi is a smooth map. Such that informally, first informal definition, the fibers of this projection pi are vector spaces. We'll speak about real vector spaces usually, so they are fibers with fibers which are vector spaces of dimension, this dimension, which is called the rank of vector bundle. Spaces over R, or shortly R vector spaces of dimension R. And the structure of the vector space on the fiber is given by the following. This is informal, as I said, explanation, but the formal explanation how to supply each fiber with the structure of a vector space of dimension R is given by the following rule, such that any point X in X has a neighborhood, has an open neighborhood, neighborhood, I also shorten this word, say U sub X, and a diffeomorphism. A diffeomorphism between pi to minus 1 of ux, that is a preimage of ux under pi, with which is so I denote this to be as a diffeomorphism. I denote it, say, by phi x, to just the product of ux times r to the power r, where small r is the rank. In this case, if you take any point, any point y in ux, then its preimage, which is a fiber pi to minus 1 of y, is mapped by phi x to y times r to the power r. So this is the same as just r-dimensional vector space. So this is R vector space, short. Vector space of dimension small r. So this is how this structure of a vector space of dimension small r is supplied to this fiber pi to minus 1 of y. Moreover, we may say, what should we say about two points? If we have, so this is not the end of this definition, just so, and for any say x and y in x any distinct points, taking pi to minus 1, taking ux, which is an open neighborhood of x, respectively of y. And if you look at the intersection, say ux intersection uy, then we have two diffeomorphisms, phi x, respectively phi y, restricted onto the preimage of this intersection. So if I take pi to minus 1 of ux intersected with uy, and respectively ux intersected uy times r to the power r. Here we have the diffeomorphism. So this is a projection pi restricted onto this. Let me denote this by W. And so this is phi x restricted onto W. Here you have the projection onto the first factor. And this, of course, this diagram is commutative by definition, since we have this before. Draw the picture, look at the picture, this picture. Respectively, we have phi y also restricted onto W. And now you have two maps, and so two diffeomorphisms. So again, they are two maps between W and itself. So let me, I am not sure that I recorded it, so I now click the recording. A smooth map, be a smooth map, such that the composition, so we have the composition pi composition S is the identity map of X. So so if I draw this picture, pi, and S is a section, is a smooth map such that this is satisfied, then S is called a smooth section, or just a section. A section of E. So if we draw the picture, E is fibered over X. So here is E, here is X, and here is the projection pi. So each fiber, if I take X, so each fiber is a vector space. So it is the same as r to the power r, a small r, and S is a smooth map such that S of X, this condition means that S of X lies in the pi to minus 1 of X. So the image of the section is a point in this vector space. So this is a vector. So the whole S is a collection of vectors, each one lying in corresponding fiber. Over that point, over which we take the value of this section. So this is S, and this is concretely it's the point S of X. So any such smooth map with this condition is called a section. Now, if we, so this is the definition of a section. So if we take any section, if S, the space of sections, let me give a notation. The gamma X E, the set of sections, set of all sections, of all smooth sections, or just sections. Of E. I would like to say that this set is actually a vector space. So the first claim is that if we take any two sections then we may define, of course, and any real number. Then we may look at the a new map called the sum of two sections. This is a map from, as any section, it is a map from X to E, sending for each X S1 plus S2 of X. I have to define this for any X. By definition, I just take it as I do with usual functions. I add them pointwise. Okay. This is the definition of this sum. Respectively, what do we mean by AS, say AS1? That is a map from X to E, sending each point X to its image AS of X. By definition, you can guess yourself, this is just A times S of X, S1 of X, S1. This is the definition of the sum of two sections and the result of multiplication by a real number. The claim is that both two maps, S1 plus S2 and AS1, are again smooth sections. That means that S1 plus S2, respectively AS1, belong to this space, the set of smooth sections. And clearly, this is the statement of this claim. You will have to check it yourself. This will be one of the problems in home task 1, which I will send you today, later when you give me your email addresses, as I announced before. So the claim is that these are again smooth sections. And of course, they satisfy all the properties of usual vector space over R. So gamma XR, XE is R vector space. And this is called the space of sections. So instead of saying the set of sections, we'll now call it the space of sections. Of course, this space is actually infinite dimensional, as you can easily guess. If X is of positive dimension, in particular, if you, let's consider the very particular case when, what is the space of sections when E is the trivial bundle with fiber R, that means X times R. Oops, it will be finished in a few minutes, I believe. So any section from X to X times R such that its composition with pi is the identity, this is the definition of a section, then S of, say, X will be a pair X and the vector in R. So say, let me just denote this by S sub X. Then if you look at the function from X to R, sending X to S sub X, this will be a smooth function, a familiar smooth function. Smooth function. Once function on X. Once, since Sx lives in R. Once S is a section that is a smooth map to here, then if you take the projection onto R, then you will obtain, so this is the second projection, projection 2 onto R. So this will be a smooth function. So any section S can be considered as a function. Conversely, if you have a function from X to R, smooth function f from X to R, then just look at the section S from X to R underline, sending the point X to the pair. The first element of this pair should be X, and the second element should be f of X. It lives in R, so the pair lives in the trivial bundle. And this will be, of course, a smooth section once. So gamma X, gamma R, so the section of trivial bundle are underlined. This is the reason why we said before, that we denote the space of functions as this, the space of sections of a trivial bundle. You see here, C infinity of X is the same as gamma X comma R underline. So, so this is the reason for this notation. So I just justified this notation that C infinity of X is nothing but the space of sections over X over trivial bundle with fiber R. So the section is nothing but the graph of the function in direct product of X comma R. That is nothing but the graph of it. That's it. So this notation just justifies the fact that any function is uniquely denoted by its graph. That's it. Okay. What is, let me say, let me give you an example of a non-trivial bundle. So say with fiber as one-dimensional space over R. So another example, except of trivial. So example of a non-trivial bundle. Non-trivial bundle over, with fiber, let me say, just R, with fiber isomorphic, each fiber isomorphic to R. Let me take for X, take this circle, S1. By the way, you know that the circle is identified with R mod integers, R mod Z. So you any point here is let me write it this way, is the class of X modulo Z. Just shortly, X plus Z. And let me take for E, R square over Z, where Z acts on R square by, so where Z acts on R square by, so once we fix number n, then it induces the map from R2 to itself, given by, I just denote this map by n shortly. X plus n and say -1 to the power n over to the power n times y. What will be the result the result will be this, as you will can check yourself. I believe many of you did this already, know this very well. The answer is called the Möbius strip. Möbius strip. This means a vector bundle, which is obtained this way. If you take a unit interval, say 0 to 1, and multiply it by R, take a direct image I times R. Then you will obtain a trivial bundle over I. So this is a trivial bundle. Let me consider the fiber over fiber F0 over 0.0 and the fiber F1 over 1. Let me distinguish among all the sections. Of course, there is one distinguished section which is called okay. So let's continue. So if I take these fibers and identify, so each of them is R, is isomorphic to R canonically. And then I identify them via this identification by the minus identity. So the vector x in R is sent to the vector minus x. So if you look at this trivial bundle and now try to identify two points in the base. The manifold X in this case is called the base manifold. So this is, just a moment. If you take this fibration, this vector bundle over unit interval, and then identify 2 points in the unit, two ends of this interval, you obtain S1. And over S1, you have to identify the fibers F0 with F1. This is the way how they identify them. So over all other points, the same fibers as in a trivial bundle. There are the same fibers as in the trivial bundle, but over the point 0, which is now identified with 1, to obtain S1 from I1, we have to identify the fibers F0 with F1. This is identified via the minus identity map. So the result is called the Möbius strip. Of course, this is non-trivial bundle because the way of identification of two fibers over ends in the over unit interval are now, so this is our E. The way how we did it was non-trivial. Okay. So this is this is the easiest non-trivial bundle over compact manifold called member strip. Okay, I think we are now approaching to the finishing of our lesson. So please, again, I ask everybody to send me his email, corporate email address to which I could send any instructions, home task, etc. I think that next time we will maybe choose not Zoom for this, but say MS Teams. But for this reason, you should have sent me your email addresses so that I could give you a link to a new system for the next lesson. If we speak about vector bundles, one more last issue. Let us have a map. So let F be a smooth map between smooth manifolds. So this will be a new definition. And let E be a vector bundle over Y. So there is defined, well-defined a new vector bundle, which is called the pullback of E over X, which is defined, so it is called the pullback of E via F or under F. As any vector bundle is by definition a smooth manifold. So we shall first define it as a smooth manifold. So let me take those pairs X and E in X cross E such that F of X, you can guess easily what you should do, should be equal to pi of E. So I take any element, any point E here, and any point X here. And then if they go to the same point under, under our maps F respectively pi, then the pair X E should belong to our F upper star E. Indeed, if you take a point Y, in Y, then and X maps to Y, so F of X is Y, then the fiber of this new projection, which I will denote, say, by pi tilde, the fiber of pi tilde over the point X, so pi to -1 tilde over X is nothing but is canonically isomorphic to the fiber of E over Y. So this means that if I have X, let me draw it below. If I have X, and if I have a map, smooth map F to Y, and over Y I have a vector bundle, then I associate to it a new vector bundle over X with fiber the same as the fiber over the image of the original bundle E. So this is projection pi, and this is projection pi tilde. So here is the fiber over the image of the point X. So this is f of X. And we just take this fiber and put it over the point X. So as it follows immediately from this definition. For this reason, this bundle is called the pullback of the original bundle E. By the way, as a manifold, the pullback, as you can see, is nothing but, please have a look, as a manifold or as a set, it is nothing, but X times E over Y. This is fiber product. So this is nothing but the fiber product as a manifold. And of course, it is a vector bundle because the structure of vector spaces for fibers of pi tilde of new vector bundle are inherited from the structures of structure of vector spaces for fibers of the original bundle. Okay, so it is time to stop now. Again, please, once again, I ask you to send me just now your email addresses and look at all my instructions, which I will send you by email. Please send your messages confirming that you attend this course and from not arbitrary address, but from corporate address. I don't like to work with arbitrary email addresses because it is not clear whose address is it. If you have certain address with extension gmail.com, etc. Please use only your email addresses with extension hse.ru. Okay, so this is the end for today. If you have any questions, please ask me. Please ask me if you have any questions. If no questions, then we have